Hello, this is the introduction of Heaps. The Heaps was introduced by Ronald D. Doughton from University of Central Florida. The paper was published on 1993. The basic rule of Wiki, there are three basic rules actually, and these are the value in any node is at least the value of any node or in its right subtree. And the second rule is the root has no left subtree. Here you can see that in this wiki, the root 50 has no left subtree. And the third rule is nodes having fewer than two children appears on the bottom two levels of the tree except the root. So here you can see that the levels where the node has only one child is actually situated in the bottom two levels. And the weak heap actually follows the structure of a binary tree. Next, we'll see why it is called a weak heap. So there are 2 points here. The first point is that it is not necessary for a leaf node to be as far left as possible. For example, here you can see that the node 14 has a child which is 9, and in the case of binary tree, this 9 should be in the left child of this node. But in Wiki, it is situated in the right side, right child of the node 14. And another point is that if any for any node, the left child has no relationship with the parent of the node. So here you can see that the node 30 and the node 22, these two nodes have no relationship. It's just left, just connected, and it's called the left child, but there is no rules to follow here. So next we will see operation of weak heap. So the first operation is the merging of two weak heaps. So there are three steps to merge two weak heaps. The first is the root node containing the largest value among the two trees becomes the root of the merged tree. Second is the smaller root node becomes the right child of the merged tree. The third is the remaining of largest root node becomes the left child of the smaller root node. Here we can see an example. There's two weak heap here. So if we want to merge these two weak heaps, first we have to find the largest root. So here you can see the largest root is 50 and the second largest root is 40. So we make 50 the root of the merged tree. Second, we will make this tree the right child of 50. Second, we will take the remaining of the largest root node, and make it the left tree of the second node of this merged tree. So this way we can merge two heaps heap tree together. uh, Next is the data structure of weak heap. So for weak heap we can use an array to store the value of the heaps. So the values of the heap. So here we can see that this heap has 7 nodes, and we took array of length 7. And for the indexing, we can follow the rules of the breadth first search. So the root will be in the zeroth index, and the second one will be in the first index, and so on. Here, to find the children of a particular node, we follow these two rules. For a particular node a of I, the left child will be the a of 2I, and the right child will be a of 2I plus 1. So here, for example, we can see that for index 1, the left child will be 2 into 1, which is 1, which is 2. So a of 2. So left child will be 22. And the right child will be 2 into I plus 1. So 2 into 1, which is 2, and plus 1, which is 3. So this the index in the third index will be the right child of this 30. But there is a problem here. Some nodes will have only one child. So for example, you can see that in the index 3 it has only one child, which is situated in index 6. But if we want to find the right child, if we use this rule, the index will be 7, and there is no index 7 here, so it will find an error. So to solve this problem, we introduce another array, which is the reverse array. Here we will store which node has 2 children, and which node has only 1 children. This array is a binary. This array is a Boolean array, and for every node we store a true value or a false value, and we use this rule to store the values. So for every index, it will be true if the right child of AI is AI of 2I, and it will be false if the right child is AI it will be false if the right child of AI is A of 2I plus 1. So for example, the node 30, here you can see the node 30 has 2 children. So for node 30, the right children, which is this one 14, has index of 3, which is actually 2 into 1 plus 1, 3. So for reverse of 1 here, we'll use we will input a false value, and for this node, which is the index, which has the index of 3, it has only 1 children, and for this children, it is in the sixth index. So it follows the first rule. because the right child is in 2 into 3 equals to 6 index. So for reverse of 3 here, we will store the value true. So for the remaining of the other nodes, the leaf nodes and the root, we will just leave empty. This is how we can store the which nodes have two children and which have only one children. So by doing this, we just updated the previous rule of finding the left child and the right child. Here, for every a of I, for left child, we will use this rule where this reverse of I, for example, if the reverse of I, if it returns false, then the reverse of I, this value will be 0, and if it returns true, then this value will be 1. And by doing this, if you want to find a particular children of a node, for example, this one index, the left child will be so because it's 1, so 2 into 1, which is 2, plus reverse of I, reverse of 1 is false. So if it's because it's false, it will return 0 here. So 2 into I plus 0, 2 into 1 plus 0, which is 2. So the A of index 2 will be the left child. And for the right child, here we can see that the index is 1, so 2 into 1 plus 1, which is 3, minus this will be 0 because reverse of I is false. So the right child will be in index 3. And there's another rule which stated that if any index, when we calculate this formula, if any index is greater than n minus 1, then the subtree is empty. So for example, here we can see that this index 3, if we want to find the value of the left child, if we insert 3 here, then 2 into 3, which is 6, plus for 3 it is true, and it for true it will return 1. So 2 into 3, which is 6, plus 1, which is 7, and 7 is greater than this length of is greater than the last index. So the last index is 6, so it returns a 7. So this left child is empty. And if we want to find the right child, here if we insert 3 in this formula, 2 into 3 plus 1, which is 7, minus because it's the reverse in the reverse of 3 is true, it returns a 1. So 7 minus 1, which is 6, and we can find the right child of index 3 in the 6th index. So next we will see heap sort, weak heap sort. So for weak heap sort, the steps are first we take an empty n-sized array, and the n is the number of nodes for in the weak heap. Next we take the root and place it at the last available position of the array. Next we break all the farthest left branches of every level into smaller heap tree. Then we merge all the tree into one tree, and then we repeat the second step again. So here is an example. This is a this is a particular this is a heap, weak heap, and we took array which is the same size as the number of nodes here. So first we take the root value and put this value in the last position of this array. Next we will break these two bonds, these two children, and make three different heaps like this. Then we will merge all these three heaps together. So first we will merge these smaller trees and make it another tree, and then we will add this merge these two trees and make a single heap, weak heap tree. So now we will repeat the process again. So here the root is 30, and we will put this 30 in the second last position, last available position, which is in 5. Then we will break this two this bond, and make two different trees, and then we will merge these two trees together. Again we will take the root and put this in the last position, last available position of this array. Then the remaining tree is divided into three trees, and we will merge these three trees together. Next we will take 14 and put it in the last available position. Next it will be 12, and then it's 10, and the remain 9. So here you can see that the whole tree is being sorted ascending order. So this is how we can perform sort for weak heaps. So this is the end of the presentation. Thank you.